Hi guys, today's going to be a nice easy day. 'Cause we're talking about the three-dimensional coordinate system. And basically everything we're going to talk about today is just an extension off of the two-dimensional coordinate system. Um, so everything is kind of just the same with a little bit of slight variation and added measure. So let's take a look. One of the first things we're looking at. Basically, how does the three-dimensional coordinate system get set up, and how are we going to look at it? It's basically the intersection of three different planes. We have the x-axis that's going to go through this way. We have the y-axis that's going to go through more horizontally, and we have the z-axis that's going through up and down. So we have to orient ourselves a little bit differently than when we're looking at two dimensions. But each of these intersections of the x and z form, their own xz plane. The intersection of the y-axis with the x-axis, that forms its own plane right here. And then the intersection of the z and the y forms its own yz plane. So it's the intersection of all three of these planes, and this singular point where all three meet, that's the origin. Just like the singular place where the y-axis and x-axis on a two-dimensional system meet, that's the origin. So let's take a look at how we are going to orient ourselves with this system. You can either have what's called a right-handed orientation or a left-handed orientation, and it basically is which way are you going to be looking at the system. Always as the z-axis pointed upward, but then how do you look at these octants? We had quadrants in 2 dimensions, but by splitting into 3 dimensions, now we have 4 on the top, 4 on the bottom. So we have these 8 octants. And how we're going to look at them exclusively when we're talking about things is in a right-handed sort of way. Octants 1, 2, 3, and 4 are going to be found by rotating. Like if you put your right hand out, you have your thumb pointing up toward the z-axis, and then if you curl your hand, that is the way that we're going to be counting the octants 1, 2, 3, and 4. So we start, and then we rotate counterclockwise, the way that you would point your fingers to find 2, 3, and 4, and then the other octants 5, 6, 7, and 8 are just directly below. So 5 is below 1, and 6 is below 2, all along in the counterclockwise way. Alright, so now let's get to the really kind of the easy stuff. Distance and midpoint formulas. Basically, I don't want to say every formula, but most every formula in 3 dimensions is the exact same thing as it is in 2 dimensions, just extended into that third part, that third dimension. So something like the distance formula, we had x2 minus x1 squared plus y2 minus y1 squared, and now just because we're in 3 dimensions, we tack on z2 minus z1 squared. Okay, so really nothing has changed about it. It's the same concept, we just have to extend it into that third dimension. So let's try one. I have this particular point, x, y, z, and I have this particular point, x, y, z. What's the distance between them? Okay, so what that means is that I have to go through my distance formula, and I'm going to do x's. I'm going to do 1 minus 0 squared. I'm going to do y's, 4 minus 1 squared. And then I'm going to do z's. Negative 2 minus 3 squared. What do I get over here? That's 1 squared, that's 1. Right over here I get 3 squared, that's 9. And then over here I get negative 5 squared, that's 25. Add all these things together, still underneath the square root sign. And what do I get with that? I get the square root of 35. And that is the distance from this point to this point in 3 dimensions. Okay? Nothing too crazy. It's just kind of adding on, making the process a little bit longer. So let's just try exercise 29. I think you'll all be quite capable of that. And once you're all set with that, we'll move on to the next portion. Okay, the next thing we're looking at is the midpoint formula, which again is going to be exactly the same. For original 2 dimensions, we took the x values, we divided them by 2. It's kind of like taking the average of the 2 points. We would do the same thing for the y values, and we divide it in 2. Now in 3 dimensions, all we have to do is do the same for the z, because we're extending it into 3 dimensions. Okay, so nothing's going to change there either. So let's say I want to find the midpoint between this 3-dimensional point x, y, z and this point x, y, z. Okay, well I'm going to take the x's and I'm going to add them together. That's 5 plus 0 over 2. And then my next point will be the y's. That's going to be negative 2 plus 4 over 2. And my z is going to be 3 plus 4 over 2. So what do I get first? I get 5 over 2. And then I get 1. And then I get 7 over 2. It might not be the nicest looking coordinate point, but that's my x, y, z midpoint between these 2 3-dimensional points. Alright, again, let's try something like exercise 45. I think you'll all be very, very capable. When you're done with that, come back and we will look at our next example. Alright, one of the most common items in 3 dimensions is going to be a sphere. That's not to say that other things like cones and pyramids and cylinders and things like that aren't common. Cylinders are also extremely, especially in calculus. But the sphere is very important, and it's very easy to see again that 2 dimensions just gets extended into 3 when we talk about the circle, the formula for a circle, and then how that extends to the formula for the sphere. The formula for a circle essentially just ignores that part. We don't worry about the z. We have a center point hk, and the x minus h, y minus k squared. Well, when we go into 3 dimensions, all we have to do is just add on that z part, and we say that the center point is no longer just hk, it's hkj, j being the z term of that 3-dimensional point. All right. So the whole situation is going to be kind of just as easy. If I want to find the equation of a sphere with a center at 2, 4, 3, radius 3, I do this process exactly the same way that I would look at a circle. I have the x minus the h, which is going to be squared, and then that's going to get added to the y minus the k, which is going to be squared, and that's going to get added to our new z coordinate parts, which is going to be z minus j squared, and that'll be equal to r squared. Now this has all been given to me, so I can easily just plug in numbers. X minus 2 squared plus y minus 4 squared plus z minus 3 squared equals 9. Right? So I know that this has a particular center point, 2, 4, 3, and a radius of 3. Okay? Again, let's try something easy like example 55. And when you're all set with that, we can look at this next part of this question. And it says, does the sphere intersect the xy plane? Now, first of all, I need to remember kind of what is the xy plane. And if I kind of draw this out crudely, that's my z, this is my x, this is my y. So the xy plane is the plane that joins together the x-axis and the y-axis. So it's this one down here, kind of like a floor in a way. And then, so I need to think. I have this particular center point at 2, 4, 3. So, 2 in the x, 4 in the y, and 3 up. So it's kind of out here in space, where it's gone 2 units this way. What is it? 4 units this way. And then up 3 units. So it's out here in space somewhere. And then I know that this thing has a radius of 3. So what's interesting about that is that I know this sphere is going to come up 3, I know it's going to go over here 3, I know it's going to go over here 3. So the whole thing is going to kind of go like this, all over, in 3 dimensions. If I had a better way of drawing that, I would. So what can we notice? Does it actually intersect this plane down here? Well, kinda you might say yes, kinda you might say no. On the next slide I have a better picture. And you can see here, this is the XY plane right down here again. You can see here that it does intersect in the sense that it touches at that particular point. So it does intersect at one singular particular point, at the point 2, 4, 0. Because if you can see this, it's 2, 4, and then 3 in the z, but the radius is 3. So that must mean this point down here is 2, 4, 0, the point where it touches that particular plane. Okay, that is it for looking at the 3-dimensional coordinate system. Good luck with those exercises, and I will see you guys later.